Hi everyone. So my name is Sumit. I'm a CCAP fellow at Ohio State University, and I'm going to bring back the conversation to supernova again and talk to you about radio observations of old thermonuclear supernova and what we can learn about progenitors from this. So typically when I give this talk, I talk about what we learn from non-detections of type 1a or thermonuclear, but a couple of weeks ago, we had the first radio detection of a thermonuclear supernova. This is in a paper by Eric Kuhl, 2022. And this was a helium-rich 1A CSM. And you can kind of see the radio detection over here. This is luminosity versus days. So basically, this is just to say that, we learn a lot from non-detections, but now it is possible to even detect supernova 1As in radio. So I'll come back to that, just to remind this for, I don't know, the 100th time that we're studying type 1As to understand their progenitors. We know it's the white dwarf that's exploding, but what is the companion is something of a mystery for decades now. The two scenarios classically is the accretion scenario, where the white dwarf has a non-degenerate companion star, could be a main sequence, could be red giant, could be a helium star. Or it could be in one of these double white dwarf systems where these two are in an orbit, they come closer as they emit gravitational waves, and then something happens, and then the type 1A happens. And then there's all these other variants we've been talking about, the D6, the sub-Chandrasekhar models, the violent mergers, and so on. I don't want to get into the weeds of this, except for the fact that we just don't really know which one of these or which combination of these are working for all the 1As. Okay, so that's the broad question. And there's many different ways, as we have heard, in which people study type 1As. You look at pre-explosion, post-explosion images, you study light curves, spectrum, host galaxies, supernova rates, many ways. And this is one of my favorite reviews on this topic that really summarizes all the observational constraints. But my favorite, and the one that I'm going to talk about, is circumstellar medium and what we can learn about type 1As from circumstellar medium. Specifically, what we can learn from circumstellar medium in radio observations. So this is the Very Large Array. This is the telescope that I typically use. And the question is why? So what's going on is that a white dwarf binary, or most accreting binary systems, is going to have some mass loss. And this can come from the non-degenerate, the red giant star, for example. It can lose winds. The accretion disk can drive a fast wind. The white dwarf can produce nova. And over time, that material or that wind is going to accumulate as circumstellar matter. And then once the supernova explodes, it's going to drive a shock into this material and accelerate electrons, amplify magnetic fields, and you're going to see that as synchrotron emission. We see this in core collapse supernova, so there's no reason to see this in type 1As if there is some matter. And the connection to progenitors to the 0th order is that in these, okay, this got cut off for some reason, but in these accreting channel, you're going to have some amount of mass that does not end up on the white dwarf. Some amount of it is going to fly off, and it's flying off at a steady rate. So you're statistically more likely to have some CSM around these single degenerate progenitors than around the double white dwarfs, which are basically just orbiting each other. You could have had some material from the common envelope episode or maybe during the merger, but overall, most of the space should be empty. That's the motivation with which people had been proceeding. And in 2010, once the VLA got upgraded, Laura, who was a postdoc, I think, at the time, and Asaf Horesh and many other people tried to follow up one of the most famous type 1As, 2011 FE, with the VLA. And this is one of the closest type 1As, and so it was expected that maybe we might see radio with the upgraded sensitivity, and nothing was seen. And this has kind of been the story for the last 10 years with almost all type 1As that were observed within a year. If you assume that the CSM could be like a 1 over r squared wind, you can parameterize the CSM with in terms of the wind speed on the y-axis and the mass loss rate on the x-axis. And so some of the closest events like 2011 FE14J, they rule out a lot of these single degenerate progenitor models, okay? And then some of the later supernovae that also went off close by, not as close as 2011 FE, kind of also rule out a lot of the red giant and some of the really fast accretion-driven winds. So I think the community kind of converged on this idea that, you know, single degenerate model is kind of struggling, or at least a vast portion of the parameter space kind of struggles to explain observations. And this is kind of showing, you know, where radio is crucial. You know, even though we're not seeing radio emission, it is still a great progenitor constraint because all of these models that are in contention would be producing detectable radio, and we don't see that. So anyway, that is an ongoing effort. But one of the things that we had been thinking about is, you know, we assume that the CSM is a wind, you know, and this comes from the idea that accreting systems are losing mass at a sort of steady rate, and so you're going to have maybe a conserved CSM, and so it'll be like a continuous system. But you can have, you know, a more shell-like CSM, you know, something from a finite episode of mass loss. Okay. So an analogy of this is core collapse supernova. So this is a type 1b, initially type 1b and then later type 2n supernova, 2014C. There was sort of emission that was going up and going down, and then suddenly it kind of bumped up because it hit this very thick shell at a certain radius. So something similar in type 1As maybe could happen. The problem is that most of the observations I told you about in radio kind of probes sort of the inner part, or like less than 10 to the 16 centimeters from the progenitor. So they're going to miss a lot of the distant CSM. So what sort of evidence do we have that this kind of configuration might exist? So for example, there are some supernova remnants, some very young 1A remnants that do show evidence of circumstellar interaction. So this is N103b. I think Ivo might talk about this later, but this is a remnant that's about a couple of parsecs across. There's bomber shells, and then there's these very thick radiative filaments that probably is coming from very dense AU-sized cloudlets. And it's kind of hard to explain that with interstellar medium, but it's plausible with a CSM. And then we've known for a while that a lot of type 1As, something like 20%, show these variable absorption lines. And if you photoionize model these, the CSM required to explain these lines should be at something like 0.1 parsecs. So that's another possibility. There has been a few of these delayed interacting supernova 1As. So this is 2015 CP from Graham 2019. And this is a system that showed up in H alpha only like a couple of 100 days after explosion, you know. And so you could plausibly explain that also with like a detached distant CSM. And then finally, kind of slightly unrelated but related, we know all these 1A CSM systems, you know. These are typical 1As, 91T-like 1As, but they have very strong hydrogen alpha lines, and that implies that there's a dense CSM wind, probably close to the progenitor, but because it's so dense, you're not going to see radio emission until much later on. And this is kind of confirmed with this new 2020 EYJ that we found, where this was a helium-rich 1A CSM, and then you see that the radio is only seen after like a 1.5 to 2 years from explosion. So there's evidence that this kind of stuff far off from the progenitor could exist. What are some of the plausible physical mechanisms? And this is where I think our theorist friends will have to help out a little more, but one plausible mechanism is common envelope. You know, if you love the double degenerate model, then you need a common envelope to actually make that, right? And this common envelope might be sitting somewhere in the distance, depending on when it was ejected, how much mass was ejected, what the ambient medium was at the time, and when these two white dwarfs actually explode. There are analogs of common envelope shells, so planetary nebula, some of them are bipolar, some of them we think are coming from common envelopes ejected by white dwarfs, and many of these are like roughly 0.1 parsec in size. So that's one possibility. Another one, if you don't like that, is the white dwarf merger events. So here you can have things like, you know, during the accretion phase or during the merger phase, you can have some material that gets ejected, and then a fraction of that might get unbound. It might, kind of hang out in the distance where potentially it could run into the supernova shock. And then one of the other mechanisms that people have often alluded to is the recurrent nova, where you have this accreting white dwarf model that continuously ejects, repeating nova eruptions. And the nova shells eventually kind of accumulate at a certain distance because you have fast novae kind of running into slow novae. And so they kind of accumulate. And this is a great famous example in M31. This is a nova super remnant, not a supernova remnant. It's like 130 parsecs across 90 parsecs along the minor axis. So, the extent of this depends on how many eruptions you've had. So it doesn't have to be 100 parsecs, could be less than that. But you could conceive of a system like this with nova eruptions, and then the 1A probably interacts with it later. So anyway, again, these things we cannot really see with any existing radio observations because all of them have been done only within 1 year. So you need to look at old supernovae to actually constrain some of these models. And also, this is a very timely investigation because we have so our collaborator, Chelsea Harris, has developed a lot of radio models assuming the CSM is a shell and not a wind. And, we've had these wind models for decades now, but if it's a shell, the evolution of the shock is very different than in a wind. And so the radio emission will depend on the width of the shock, where the width of the shell, where the shell is located, and then how dense the shell is. Okay. So basically, I'm just going to report some of the supernovae that we have tried to investigate so far. So this was from a paper in 2019 where I looked at one of probably the oldest supernova that we know of, oldest supernova 1A that we know of, 1885A. This is an M31, and it's actually really beautiful. You have the you can see the ejecta, calcium, iron, and absorption. And we tried to get radio observations of this. This is one of the deepest observations we have for a 1A. And we didn't really see anything. There is kind of a 2 sigma detection. We might have to follow this up in 10 years and see if it actually becomes 3 sigma or something. But if you treat this as an upper limit, it's very low density, kind of similar to the ISM of M31. And then Yvette and Maria Drought followed up some of these 1895B and 1972E supernovae at 3 megaparsecs. Again, nothing was seen, but we were able to constrain with Chelsea's models that if you have any CSM shell, it should be less than 0.05 solar masses. The problem is that the emission of radio depends on how thin the shell is, and also where what the mass loss history of the white dwarf is. And so this means that we need to look at a lot of supernovae to really constrain the parameter space of shells. And so this is kind of an ongoing project where I'm looking at all the 1A supernovae that have gone off in the last 100 years and trying to kind of constrain that. So I think I'm out of time now, so I'm going to leave off my summary. And I just want to say that I think this is a very new territory that I think anybody who does 1A modeling from white dwarfs should really get involved. There's very good observational constraints that we can get. So thank you so much.
Thank you for the talk. Chris has a question.
Hi, Sumit. Great talk, very informative. I had a question, which is planetary nebulae is about like 10 to the 18 centimeters across, and in a year you're probing 10 to the 16 centimeters. So you can imagine that maybe in 10 years' time you should already be probing planetary nebula material, and there are a lot of type 1A supernovae that are relatively well observed that have been around for like 10-year-ish periods. Mm-hmm. So do you think those would show the kind of planetary nebula interactions?
Yeah, I mean, so in the radio, I won't really know if it's a planetary nebula or something else. I'll just see like a radio detection. And so, yeah, like conceivably, if they do run into like a common envelope shell of some density X, it'll show a proportional amount of radio in 10 years. That's kind of that's sort of what I'm trying to do here.
Thanks.
Yeah.
So at some point you should just start sweeping up enough material to make a remnant, right? Like, 300, 400 years. But for the 1885 is, a little more than 100 years ago, but there's still no detection. Is it just too far away to, like, if it were to have swept up something like, more like Tycho or Kepler, would we be able to see it at the distance of M31?
Yeah, I mean, yeah, so G1903 is a supernova remnant, like the same age as Tycho, and that has radio possibly coming from swept up ISM. So that would be detectable at 1A, at M31 distance. I'm not sure if you will see it at 3 megaparsecs, but at M31 you should see it. So the fact that we don't see it with 1885A means that the ISM is just low density.
Sorry if you already mentioned this, but how are you choosing your sample? Because there are like so many supernovae that 1A supernovae that are 1 year old, 2 year old. Do you have a distance threshold?
Yeah, so it's 30 megaparsecs.
Okay.
And then beyond that, we don't think the limits would be constraining.
Okay, thanks.
Hi, that was a really nice talk. For early observations of, say, 1A CSM, even just normal 1As, do you have any reason to point radio observations at early time? Like, as if you were just to give advice, like, is there any reason why we should have programs for early radio observations of 1As, for 1A CSMs, for anything thermonuclear with CSM around it? Or is it just, there's no point in submitting those proposals?
Right.
So if we just keep getting non-detections, then, which is what you expect, then yeah.
Yeah, so there's a couple of answers there. So 1A CSMs are probably not useful to observe within a few weeks, because if the H-alpha observations are correct and if the models are correct, your mass loss rates are incredibly high. I mean, we don't know why some of the mass loss rates are like 10 to the minus 3, which like is way higher than what you get from red giants. So there's problems there. But if it is that dense, then you're not going to see radio within a few weeks. You have to wait at least, I don't know, a year or two. For 1A, normal 1As, I think it is at least statistically still useful to look up, to just, get all of the constraints, because you can put population constraints on what fraction of them have X amount of CSM, and that's still a useful information for progenitor models. One of the things we tried to do was actually follow up some of these like early bump supernova 1As in radio, because we thought that if it's CSM, then that might show some radio emission, if we got the radio within like a day. But we couldn't find them, and I think some of the CSM densities are really high, so maybe there's a problem. So yeah, I would say for normal 1As, it's not a bad idea,
Okay, cool.
Yeah, Ivo Seitenzahl here. Thanks for your talk. It was great to see. 1937C might be another great target, I think, because it was pretty normal, unlike 1885A, which was kind of weird and subluminous. And it's maybe at a good age as well, right? Just under 100 years. Have you looked at that one or thought about?
Yeah, I think 1937 is in one of these. It may be in one of these data points here. Okay, I'm not showing that. But I think, if I remember correctly, is 1937C in an AGN?
I don't know.
Okay, I think because one of those 1937 targets is like in a big like radio galaxy, and that washes out the radio. So those are kind of unlucky. But there's a lot of like 1930s, 1940s targets.
All right, I think we're out of time. Thanks, Sumit.